All right, everyone. How are we doing today? All right. It is Monday. Now that I sit down here, I feel like I'm overdressed. It's chilly outside. It is kind of stuffy in here. All right. Anyway, we'll be okay. Uh, and then one of your classmates in the chat says they're feeling a little stressed, which I can understand. Huh? Yeah. I'm in the same boat, unfortunately. Trying to catch up, but it hasn't been easy. All right. Well, I wish you all well. Is this one of those situations where, like, all of your classes decided they were going to have exams at the same time? Okay. Yeah, there tends to be at least one time a semester where that just happens due to the way that things shake out. Uh, you know, the due dates on the quizzes have generally been flexible, so I'm not gonna worry about 1 or 2 days. So, if maybe. Yeah, I think the one that I assigned for this past weekend, I'd actually made not due Tuesday. Yeah. So that one's the current quiz has extra days built in. Yeah, maybe. The exams that you have taken, I'm going to try as hard as I can today to enter as many grades as possible. That's one of the things I wanted to address. I had intended to get some stuff entered this weekend, but uh, I'll just say personal life got in the way. Or I wanted to, it didn't work out. I apologize for that. So the exams, the first exams will be put in. They may not post until tomorrow morning, but I'll have that in so that if you need to make decisions about things tomorrow, you can. The reason the question was asked, of course, is that I think tomorrow is the last day to withdraw with the W or whatever the politically correct phrasing for that is. But I was trying to catch up and didn't get to do that, and I apologize. Okay, but our business for this week is to prepare for our Chapter 15 exam on Friday. Just as a note for my online students who aren't in who watch these videos anyway, um, you don't have a separate chapter exam here. We just have the final for the other class. So obviously you can watch the videos, but don't think that there's an exam for right now. Okay. So there are basically two ideas that kind of go overall for the chapter that we've been covering here, chapter 15, and that is double and triple integrals. That's the focus, okay? And the textbook breaks up several sections in the chapter into these two broad categories. Okay, so obviously the exam is going to be focused on asking you to demonstrate the different skills with respect to these disciplines. Okay, so what you should expect we'll just call this a box because it's easier to write box than it is to write rectangular prism. Okay. So these two types of integrals are related. They are the ones that are the most straightforward. Okay. A rectangular region is going to be defined like this, okay? And a box region or a rectangular prism region. Obviously, box isn't a technical term. I'm just using it because it's easy, okay? But it's the Cartesian product of a collection of intervals, okay? It is extremely easy in both of these cases to set up an iterated integral, and in these regions, you can change the order of integration to be any order that you like freely. Okay, you can use Fubini's theorem without having to do anything complicated. Because all you do is just switch the integrals around and then integrate with respect to a different letter first. Okay, so you would have the integral from a to b and the integral from c to d of f of x, y, sorry, dy dx. And that's going to be equal to this integral. Okay. Over here, you have the same thing, except there's 6 different ways to write it, and I'm not going to bother doing that. Okay. But you can freely change these things. Everything's nice. One potential question that I could ask you for this or for any triple integral situation would be, as kind of a short answer question, I give you a version of an iterated integral and then ask you to give me some number of equivalent iterated integrals. Okay. In this case, there'd only be one answer to that question, right? But here, if I give you one, there might be 5 other ones that you could write down. Okay, I may ask you for 2 or 3. Okay, I could also do it, of course, with a general region, something where I give you, say, a triangle, write down an iterated integral for it, and then ask you to give me, say, 2 equivalent integrals in different orders. Okay, so more of a geometry type question, setting things up right, than a compute this integral type question. All right. One of the, of course, major components of the section is being able to make those sketches and be able to, if you need to, change the expression of a curve to be a function with respect to the other variable, okay, or another variable. I haven't fully written out the exam yet, but my plan is, and I will change my plan based on what I feel are the needs for the exam, is that I may give you a sketch of one of these things at one time and then ask you, say, to change the things around so it's not a question where you lose time because you're worried about drawing the picture right sort of stuff, to where I give you a picture and it's your job to interpret it, which is the main thing. Or I could ask you in what would ultimately be a simpler region to produce a sketch based on what I would tell you that the iterated integral looks like and ask you to switch. Okay. And for a problem like that, what I will do is to not overload the points on something that there would be like a failure point in the problem, i.e. not setting it up correctly. The questions I will separate out into set this thing up or change the order of integration, and then the computation questions are going to be more computationally focused. Okay. So I'll try to split that so that it's not a, like, you don't get the first step on the page right, so you can't answer the second 2 questions. Okay. All right. So I'll make a note of this. So this is more geometry focused there. Okay. All right. I don't want to not write this on the page, so I will make sure that it's added here. Of course, there will be straightforward computational questions in addition to this. I want to write that down before we start talking about the next thing, which is our different coordinate systems. Okay, and then of course, this obviously counts for both. All right. One of the things that may come up in one of the problems that I ask you to do would be to compute an integral in polar coordinates. Okay. Most of the time, these things arise in applications or in situations where you find them as not necessarily immediately presented in polar coordinates. Okay. So one of the things that you need to make sure that you're on the lookout for is if you see an integral that looks like it would be a lot easier if you change coordinate systems, the intent is for you to probably change the coordinate system. Okay. As long as what you're doing is correct and executed properly, that is what I want to see. Okay. The thing that you add as a problem solver and an observer when you are working on these things in roles, say as an engineer or further along your careers as students and things like that, is having a knowledge base that allows you to recognize the pattern that says there is a simpler way to solve this problem than the way that it is expressed. Okay. This is why we do things like change the order of integration or change the coordinate system that we are evaluating things in. Okay. We all know that we can't actually do the analytical calculations faster than computers. Okay. But computers have not yet reached the point to where they can interpret language and recognize patterns as well as we can. All right. So part of the reason why we have classes like this and a lot of the other undergraduate sort of survey courses and onboarding situations and basic training for engineering or science or physics or whatever it is so that you can have that knowledge base to see something and recognize, okay, hey, I've seen this before and I know that there's a better way. Okay. I don't have to slog through this nasty algebra and deal with these x squareds and y squareds that show up. Okay. There's something that I can change these to that makes this easier. So there may be one or two problems on the exam that are presented in a way to where I don't tell you that you should change the coordinate system, but if you start working on it, you're going to realize that it's really irritating to try to solve this problem, and that's likely an indicator that you're not getting anywhere, so you should have changed the coordinate system. Okay, so I wanted to say that because this is the one thing that's maybe on the exam presented in a somewhat confusing way, or it is not obvious what the path is, but that is how you will encounter it practically. And so I believe that that should be reflected. Okay, so we have one major coordinate change for double integrals that show up, which is polar coordinates. And for three-dimensional coordinates, we have two major coordinate changes. Okay, different coordinate systems that we work with. It is paramount that you remember the Jacobian. Okay. When you change coordinates, it introduces a factor, and we have to remember to put it there. Okay. All right. Oh, and there's one thing that I want to point out as a follow-on from Friday's lecture, where I was all over the place talking about spherical coordinates. Okay. I had mentioned the issue with physics texts and mathematics texts tending to use the variables theta and phi to represent the azimuth and the polar angle at different points. And that's definitely the case. But part of my confusion, I realized a few minutes after class had ended, was actually spurred by the fact that your book is extremely inconsistent about the way that it writes the d theta d phi stuff. It switches them, okay? And it will switch them for problems where you are integrating over the entire azimuth. So if the azimuth goes from 0 to 2 pi, most of the time, um, the theta factor here, you're just integrating over the entire circle. So you get the situation where you have the integral from 0 to 2 pi of d theta and then the rest of it. Okay. And so if you look at the examples in your textbook and you're reading problems and you see that the d theta and the d phi end up being written in different order sometimes, that is often why. Okay. And of course, I was caught in the funny headspace about the math versus physics versions of the notation, and I thought I was making mistakes. I didn't realize that it was something that the book was also partially responsible for. I was screwing up too, but I'm not going to take full responsibility. So, all right. Questions about this so far? Okay. The final thing, and this idea is connected to both halves, all right? It's not specific to double integrals or triple integrals, it's just a fact of coordinate systems in general, and this is the idea of the Jacobian. Okay? If you look at our schedule for today, we are actually supposed to technically talk about section 15.9, but 15.9 is really connected to general coordinate changes. Okay? And the idea behind the Jacobian is that it allows us to encode the scaling change when we switch coordinate systems. Okay? Our basic integration regions in 2D and 3D coordinates are squares or cubes or whatever, right? And what we need to do is if I change to something like polar coordinates or cylindrical coordinates or spherical coordinates, I'm going to have some kind of deformed object, all right? And if I take these side lengths to be 1, I have to know what happens to the area of this shape as a result of that, right? So maybe these things are 1, and this is 1, and this ends up being R, or who knows, okay? That's not actually what it is, but I end up here with the area of a truncated circular. I have a sector of an annulus, is what I have. Okay. The sector of a circular sector, by the way, is like a pizza slice or pie slice. Okay, that's actually a technical term. So when I say sector of an annulus, I mean cutting off a smaller concentric circle. But turns out that the difference between these two shapes is dependent upon the radius. Okay. And for these, the scaling is, in this case, very similar because one of the dimensions stays in rectangular coordinates. So the scaling is unaffected. And then this, we went through and computed the Jacobian to show what was going on with this. Okay. I may ask, and this is on the maybe list for problems that may show up on the exam, is I may ask you to do a coordinate or to compute the Jacobian for a different coordinate system change. Okay. So what I would give you and this could also be in 3D, but I'm just going to write the 2D version. Okay. Sorry. This should be a different letter. I would tell you that x and y equal some new functions in terms of a new variable. Okay. We've seen this sort of thing before where I would tell you, say that r equals r cosine theta and y equals r sine theta. Okay, that's the transition to polar coordinates, right? This is what I mean. That's all I mean. And what you would want to do is to compute the Jacobian of that coordinate transformation. Okay. And so what this would give me is the scaling factor that encodes whatever's going on with this coordinate transformation. Okay. You could also get the 3D version of this where you have a larger determinant to compute, but I'm probably not going to ask you to do that just because it takes a lot of time, and very rarely do they have the nice symmetries that something like the spherical coordinates Jacobian had to give you this nice condensed form. So, but this sort of thing is important because it allows us to use any coordinate system that we would like. Okay. You may, if you were doing something in a specific engineering application, may have a reason to switch to skew coordinates. Okay, where things aren't necessarily orthogonal. Okay. Maybe this isn't terribly likely, but it's a thing that can happen, right? Okay. And what you would need to do is if you're computing derivatives or computing integrals in this environment, you need to know if this parallelogram that you have now is deformed in a way that changes the value of integration in this coordinate system. Okay. So you could see what was going on here. Another thing that's perhaps more likely is if you change coordinate systems to be something like relative to an aircraft. I'm always nervous when I try to sketch things. Okay, so we have our aircraft here. And we have a coordinate system that is like this, okay? But the thing that the coordinate system cares about are these rotational axes, right? Okay, so we have a coordinate system that moves with the aircraft, and if I have to do integrals in this context, maybe I have to be careful about how this works because these things are all encoded in rotational matrices. So you could go through and do the mathematics necessary in order to track everything that was going on through how the rotational coordinates work and all of that. Okay, as another example of a place where you may encounter this sort of thing. Okay, the point is that the Jacobian always works. Okay, it is a hammer, and any coordinate change would be our philosophical nail, right? Okay, so in terms of content, that is what the exam is going to be mostly focused on. Okay, now one thing that I haven't mentioned yet that I do want to bring up, because I may use the vocabulary from these sections, would be from our application chapters. Okay, or the application section. We had 4 primary applications. All right. So the applications here were primarily focused on looking at, or at least, sorry, these first 3 were all focused on lamina. Okay. A lamina is some thin sheet. Okay. You can imagine it as like a thin sheet of plastic or something like that. It is a 2-dimensional region whose width is inconsequential for the purposes of calculations. Okay. If you were trying to, it's. Have any of you ever worked with Lexan? Okay. So Lexan is, for those of you who aren't familiar with what I'm talking about, is a thin, clear plastic. Okay. It is occasionally used for molding or modeling. My experience with it is when I was young, my dad used to race what are called slot cars. Okay. But they weren't the versions that most of you are probably familiar with, which are called HO cars that are kind of like tiny Hot Wheel size things. The versions that we raced were 1/24th scale. So they were the size of models that you would kind of need 2 hands to comfortably hold. You can hold it in one hand, but the car would be bigger than your hand. If you hold it in 2 hands, your hands would be slightly larger than the size of the car. So if you see a bunch of modeling kits for like NASCARs and things like that, those modeling kits tend to be the scale that we're talking about. Except instead of using models most of the time, what we would use are Lexan body cars. So there would be a mold that would be made, and then the Lexan would be heated up and then press molded on top of the mold, and the body of the car would be made out of this thin material that had been molded and stretched. Okay. If you were trying to figure out how much that stuff weighed, okay, or how much mass it had, it doesn't do you any good to measure the thickness of it, right? You just measure the area and then base the density of the material on just what the surface area would be, right, for a particular region. So approach lamina the same way. All right. When you hear the phrase lamina, just imagine a material like paper that is so thin. It's just, this is a thin thing, and the only thing that I really care about is its area. Okay. Now, in the computations that we do for these applications, if we're computing something like mass or center of mass or moment of inertia, we are operating under the assumption that there are variable densities on the plastic. Okay, so you can imagine there are imperfections in the material. It's not equally dense the whole way through when it was manufactured or something like that. Or if you imagine, another thing that you could think of as a lamina would be, say you have a cake and you are frosting the cake. Okay, you have a thin layer on something, but you're not necessarily going to have the entire stuff be uniform, right? Okay, there might be little pits and divots in it as you're spreading it out, or if you have this kind of frosting like you would put on a donut, where you heat it and just kind of pour it and try to get it to lay thin, it's not going to dry in a way that is homogeneous, okay, or homogeneous. We always mess this up. You homogenize, homogeneous. Anyway, this is the sort of thing that we're talking about. All right, there are small densities not related to the thickness of the material, just kind of fluctuations. And so if you want to measure the mass, you have to incorporate that and when you compute the integral over the region. Okay, so this is what the function rho represents, are those small variants, in general, small variances. So we have our double integral, we have our function rho, and dA. And so this would be the mass. Okay. And there are other formulas for the first moment and the second moment. We talked about those previously. You can look those up in the text. Okay, but be prepared for those if I use those vocabulary to compute those. You can, by the way, have a one-page note sheet with the same rules as last time. Come on. Okay, so rules are the same. You're allowed to have formulas and definitions and explanations that are written out to yourself. If you want to have like a couple of sentences to remind yourself how to set something up, that's fine. What I don't want to see are worked problems. Like, don't set up and then set up a different way, an iterated integral or something like that. That's outside the bounds. Yes. Thinking about that. I'm weighing that against the fact that there's only 50 minutes to take the exam. Would you mind asking me about that on Wednesday as a double check? So I'm leaning towards maybe not, but I don't want to commit to that yet. Let me think about that a little bit more. Yes. I'm also thinking about that. Huh? They can. All right. So I will answer that question as a probably, and it would be something that would be due like early next week. Okay, so like Tuesday at the earliest. So they give you extra time on the other quiz and something like that. So uh, we'll go with probably, and then likely what that would look like would be a moderately challenging integral to do, since it would be something that you would have plenty of time to work on. Probably one of these application type questions where I ask you to go into a little bit more detail about stuff, compute all the different pieces, and maybe one other thing. So in the neighborhood of at least two, probably three problems. Okay. All right. Where are we on the rest of this? Okay. Now some of the stuff I'm probably not going to be able to get to until Wednesday, but just in my mind, so that I can prepare mentally for this between now and next class. Um, out of the topics that we have discussed and listed out and put everything together for and may appear on the exam, other than triple integrals, because I know that's what everyone's going to ask about, what is there something specific that you want to see more of on Wednesday? Polar coordinates? Okay. All right. Okay. All right. So the two questions for posterity's sake and for those of you listening, uh, folks asked me about solving problems in polar coordinates and then also solving doing a probability application problem. Sorry, I'm trying to find if there's an easily identifiable problem in the review for polar coordinates stuff. Okay, sorry, I might have to look in the actual section for that. Okay. Also check the chat so I don't forget to do that. Should be okay over there. All right, sorry, I was reading. I apologize for the dead air there. Or are we on time? Okay. All right. So we want to find the volume of a solid that is bounded by we're going to be below the cone. Z equals the square root of x squared plus y squared. And above the ring, that is given by 1 is less than or equal to x squared plus y squared is less than or equal to 4. Okay, so we're given this in Cartesian coordinates. We want to convert to polar coordinates and be able to compute the volume of this region, right? So let's start by trying to get a handle on what this region may look like, at least a bit of it. Okay. So let's turn off the straight edge here. I'm doing my best to try to draw this in perspective. Okay, this is all, that's in the XY plane, right? I'm trying to draw this. Okay, so we have that. And then for Z, we want to go below this cone. And this cone should open up like this, right? That's probably not to scale, but that should be how that works, right? Does that make sense? Okay. So the region that we're going to have is going to be where this cone connects down to the surface, right? So the shape would be something that looked like this to start off with, okay? Except it's hollowed out here. Or, whoops, sorry, that actually starts all the way at the bottom. Does that make sense? I know the drawings are terrible, okay, but that's the idea. All right, you have a kind of a donut shape, right? And for that donut shape, what someone has done is they have taken a drill that is this shape and then drilled down until the tip of the drill touches the center part of where the donut is. And you're left with the rest of the material. Okay. So we want to set up now our integral in polar coordinates. And the way that we do this, of course, is by trying to represent x squared and y squared in terms of polar coordinates. So we write x squared plus y squared equals r. This, of course, means that z is going to be equal to r, right? And what this allows us to do is set up the double integral here in polar coordinates. We're integrating the function 1 because all we care about is the volume of this region, right? We're integrating over the entire circle. Hold on, I want to make sure we get this right. Okay, sorry, I made a very small mistake. I was thinking about this as a three-dimensional integral. We can't quite think about it as a three-dimensional integral. I will write it both ways. How about that? Okay. The problem as presented in your textbook is from the section where we're just talking about polar coordinates. So the way that we construct the integral looks like this. The theta is going to go from 0 to 2 pi because we're, of course, integrating over an entire radially symmetric region. the integral with respect to r is going to go from 1 to 2 because we think about r squared as being 1 squared is less than or equal to r squared is less than or equal to 2 squared. Okay? And the function that we're integrating is z equals r because we're going from z equals 0 to r as our height. And then we have RD theta from the Jacobian. Okay? Never forget the r that comes from the Jacobian calculation there. Okay? If I were setting this up as a triple integral using cylindrical coordinates, which is another valid way to approach the problem, it looks almost identical except you would write it like this. Make sense? Okay. So sorry that when I misspoke earlier, this is what I was seeing in my mind's eye because that's how I'm used to thinking about it. But we can also just approach it as a 2D problem. Okay. From here, the mechanics of solving the problem are simple. This integral can be computed separately because there are no thetas that appear in the integrand or the limits of integration. So we're going to get 2 pi times... Sorry, what? You're right. Thank you. Okay. And so that is what the computation will look like in this case. All right. If there's a specific example that you would like to look at from the textbook or something next time, maybe one where we have like a partial region for the polar part or something, just tell me. I have access to the textbook here, so you can just tell me like what problem is out of the text. We can take a look at that too. Okay. All right. So we're out of time for today. Thank you everybody for being here. And if you do have specific questions, again, for everyone, if you can ask those next time or say, hey, at the top of the hour, say, hey, can we do one of these? We'll try to work in as much stuff as we can. All right. Take care.